This is lecture video 49, and in this lecture, we will try to understand trigonometric substitutions. Trigonometric substitutions occur when we replace the variable of the integration with a trigonometric function as follows. So most commonly used trigonometric substitutions are the following ones. For example, if you have this inside your integral, this type of function, then the trigonometric substitution that you should use is a times tangent theta. Why we call it as a trigonometric substitution is because now our new variable is theta. So x is the original variable of the integration, but the new variable is theta now, which means we will be solving an integral. After doing the substitution, the integral will contain only thetas and d thetas. So the new integration will be with respect to theta. Okay, this is our new variable now. Then you should solve for dx, of course. What is the derivative of tangent theta? It is secant square theta d theta. Okay, so whenever you have this type of function inside your integral, you need to use x equals a times tangent theta substitution. So instead of the variable of the integration, which is x, the original variable, now we are inserting a trigonometric function depending on theta. The new integral will depend on theta and d thetas. Okay, so the most common used ones we were talking about, if you have a square minus x squared here, if the function is of this type, then the trigonometric substitution should be a times sine theta, then dx is a times cosine theta d theta, of course. And if you have this type of integral, like x squared minus a squared dx, then the trigonometric substitution should be x equals a times secant theta, then dx is a times secant theta tangent theta d theta. Okay, so these are the most commonly used trigonometric substitutions. When they are used, you use them if you have integrals of this type. And here, you don't need to have this structure just on the denominator like this. You may also have it in the denominator, for example, a squared plus x squared, or you may have other powers of this square root, for example, dx over a squared minus x squared 3 over 2. You see, this is the third power of the square root, and it may also appear in the denominator, okay? And also, for example, let's give this one here, x squared minus a squared cubed. This is another way of writing this expression with the square root, right? So these type of forms may appear also in different forms as I exemplified here. May appear also like this. Okay. So these are the cases that we may have to use trigonometric substitutions. Mainly, there are 3 types of trigonometric substitutions most commonly used. And we also need to understand the reference triangles. We will be using them to turn back to our original variable x after integrating. You need to turn back to x, and you will be using this reference triangles to write your original variable x. Okay, look at the first triangle. Here, if you use this trigonometric substitution, then by reading this in this form like tangent theta is x over a. By reading this equality, you can easily draw your right triangle, giving you this tangent value. So how do you do that? Tangent is what? Opposite edge divided by the adjacent edge. So these two edges are used to obtain tangent theta. That's why these two are pink, because they are used here. And if you have x here, a here, then the hypotenuse will be, of course, a squared plus x squared. Okay, let's use another color for the hypotenuse because it is the result of what you have here. And if you consider similarly for this case, okay, what you have for sine theta here, this is your trigonometric identity. And then the right triangle should be drawn like this, of course, where theta is here. Then sine is opposite edge divided by the hypotenuse. That's why we are using these two edges. That's the reason these two are pink. So the remaining edge of this right triangle can be solved like this. And similarly for the third case, you read secant theta as x over a here. Secant theta means 1 over cosine theta, right? 1 over cosine theta is x over a, so cosine theta is a over x. By reading this information, you can easily draw a right triangle of this kind, where theta is here. This is adjacent edge divided by the hypotenuse. That's why this part can be solved as this square root. These are called reference triangles, and you will draw them by using your trigonometric substitution like this. Okay, let's move on. And here, there are some restrictions on theta to have a well-defined inverse function. So these are the trigonometric substitutions that we have talked about above. And here you can solve for theta easily. How do you do that? From this line, you solve tangent theta as x over a. And if you apply arctangent to both sides, and what you have, arctangent theta is given by, obviously arctangent and tangent will neutralize each other because they are the inverse functions of each other. That's why you only have theta on the right hand side, where you have arctangent x over a on the right hand side. So, you know, your course book uses tangent to the power -1 for the inverse trigonometric function arctangent. So, and do you remember the graph of arctangent function? Let me draw its graph for you. Its images takes values between plus pi over 2 and minus pi over 2. And the graph behaves like this. As you can see, the images of arctangent function change between minus pi over 2 and plus pi over 2. You see, this is the image of an arctangent function. That's why theta should lie over this range set, right? So theta should be between minus pi over 2 and pi over 2. Why it is like this? Because it is the image of the arctangent function, where you know the graph behaves like this. The images are between minus pi over 2 and pi over 2. Okay, so these are the restrictions, similarly also for arcsine and arcsecant, which are covered before in the section where we cover inverse trigonometric functions. We write all those restrictions on theta as theta being the image of this inverse trigonometric functions. So these are the important restrictions on theta to have a well-defined inverse trigonometric function in each case. Okay, so after covering also these restrictions, why they are important, then we can start solving some examples. And to solve integral questions by using some trigonometric function, here are the steps that you should follow. First of all, you will write down a substitution for x depending on the trigonometric function that we have covered above. So what are the most commonly used trigonometric substitutions for x. So you may either use this or this one, or secant equals a times x equals a times secant theta. These are the trigonometric function substitutions that you can use. After writing this, you will also compute dx. And then you will try to write your function in integral in terms of your new variable theta, okay? So how do you do that? You will substitute these trigonometric expressions into your integral. And then after obtaining an integral, when you do that, you transform your integral in terms of some function depending on theta and d theta. So this will be, theta will be your new variable. After transforming your integral like this, you will integrate it with respect to theta, okay? Integrate the trigonometric integral, and then you will draw your reference triangle. Why you would do that? To turn back to original variable x. Back to original variable x, you will need your reference triangle to write the result in terms of x. Okay, these are the summary of the steps. Let's follow these 4 steps in this example. So look at the integral and look at the form here. This form fits to this form, right? A squared plus x squared form. And remember which trigonometric substitution is used for this kind. Okay, the trigonometric substitution is a times tangent theta. Okay, let me show you. Here are the most commonly used structures. And if you have a squared plus x squared, you use a times tangent theta. And what is a here? You see, this part corresponds to a squared. That's why a is 2. That's why you will be using this trigonometric substitution, which is 2 times tangent theta. And then compute dx. It is 2 times secant squared theta d theta. Okay. And then you are ready to rewrite your function in terms of theta and d theta. Dx is this line. You directly insert that line for dx, okay? So this is written for dx part. And what you have at the denominator, let's see, it is 4 plus x squared, where x is written like that. 2 tangent theta square. Okay, I inserted my substitution for x here, and then what you obtain here is, it is 4 parentheses 1 plus tangent square theta, and remember the trigonometric identity for this part, it is exactly secant square theta. That's why the denominator here, which is the square root of this expression, is in fact square root of secant square theta. So this thing is in fact just this. And normally also there is this 4 in front, and normally this is evaluated as with the absolute sign. But because of those restrictions on theta that we assume at the beginning to have a well-defined inverse trigonometric secant function, you can get rid of these absolute signs because secant will be positive there. So the result is 2 secant theta for the denominator, okay? So what you have for your integral then? Then this integral is, okay, let's rewrite the denominator as it is. What we have at the denominator is this expression, just 2 secant theta, okay? Okay, then you have very nice simplifications so that the integral looks like this one now. Integral of just secant theta d theta. And you know how to integrate secant theta. We have a rule for it. The rule goes like ln secant theta plus tangent theta plus an arbitrary constant c, because it's an indefinite integral. But you shouldn't stop here. You should turn back to your original variable x. Back to original variable x. How you will do that? You will be drawing a reference triangle, which is given here. This is the reference triangle that we should use. How do we draw it? Because here you see that tangent theta is x over 2. So how do you draw a right triangle? By reading this trigonometric function. Tangent theta is opposite edge divided by the adjacent edge. So these two pink lines, that pink edges, gives you this tangent value. And then the hypotenuse is obviously 4 plus x squared square root, theta is here. That's why from this triangle now, reference triangle, you can easily read secant theta and tangent theta. What is secant theta here? Secant theta is in fact 1 over cosine theta. So 1 over, what is cosine theta? It is 2 over the hypotenuse, right? So secant theta is 4 plus x squared square root over 2. 4 plus x squared square root over 2 plus what is tangent theta? It is x over 2, obviously. And that's how you should turn back to your original variable by using your reference triangle. Back to x, we do this by using reference triangle. Okay, so our result is given by this expression, which is in terms of x. Okay, let's do one more example by using trigonometric substitution. Again, you need to detect the structure. The structure is in this form, a squared minus x squared form. And for this case, we are, with trigonometric substitution, we should use x equals a times sine theta. So what is a here? A squared is 9, so a is 3. That's why the trigonometric substitution that will work here is x equals 3 times sine theta. Then what is dx? Dx will be 3 times cosine theta d theta. Then, according to this trigonometric substitution, you can rewrite your integral as x squared, x being 3 times sine theta, square, what is dx? Dx is written here, cosine theta d theta, divided by 9 minus x squared, where x is 3 sine theta squared, right? Okay, let's deal with this denominator. It can be written as 1 minus sine squared theta, where you can write 1 minus sine squared theta as cosine squared theta. So the denominator is, in fact, 9 cosine squared theta, which is 3 times cosine theta in absolute sign. And as I explained above, you can get rid of these absolute signs because of our assumptions on theta given above. So the result for the denominator is 3 cosine theta. And then what we have for the integral is the following. It is, okay, just compute this square too. 9 times sine square theta, 3 times cosine theta d theta, and denominator is just 3 cosine theta. Okay, let me just put some details here. This is written for dx, this part is written for x squared part, and the denominator. So you can simplify these two, and you just have what? 9 times sine square theta d theta. 9 goes out, and how do you integrate sine square theta? We covered this in the previous lecture videos. You will insert half angle formula. Because the power is even, you need to insert this half angle formula for sine square, and then you can integrate it. It is done. 9/2. I take this 2 out from the integral. What is the integral of 1 with respect to theta? It is theta minus integral cosine 2 theta. So it is integrated as sine 2 theta over 2. And then you need to put an arbitrary constant c there because you are dealing with an indefinite integral. And for this thing, you can put this trigonometric equality. Now it is time to turn back to the original variable x, right? So you need to look at your reference triangle now. Okay, so remember the first line of substitution, which is here. So let me write triangle. Okay, so we use this. So we are using sine theta equals x/3, right? That's why, what is sine? Sine is opposite edge divided by the hypotenuse. So if theta is here, I should write x here. That's why hypotenuse should be 3, so that you can compute the remaining edge like that. And here, remember, we need to turn back to x, and we have just theta here. That's why we should solve for theta. How? By taking arc sine of both sides to just left with theta on the left side. Okay, then you have what? Arc sine x/3 is theta. Okay, so I started to turn back the original variable x. 9/2 theta is arc sine x/3, right? And here we have 2 times sine theta times cosine theta. Both can be read from this reference triangle. Sine theta is x/3. And what is cosine theta from this right triangle? Okay, cosine theta is this adjacent edge divided by the hypotenuse, like this. So the result is minus 2 times sine theta times cosine theta plus c. So that's how you should turn back to your original variable x. Back to x by using reference triangle. Okay, so our final example is here. Then I stop for this lecture video. Look at the structure. Which structure does it fit? It fits, I think, x squared minus a squared structure. So x squared minus a squared. Once you have this, you use which trigonometric substitution? You need to use x equals a times secant theta substitution. But you should be careful about something, because in your function here, instead of just x, you have 5x squared, right? So let's try to match things. If you have 5x squared minus a squared, then instead of x, what you do here? You just put 5x, right? That's why this will be used for the trigonometric substitutions. By the way, what is a here? It is 2 squared, so a is 2. Let's insert the value for a here. 2 times secant theta. Okay, so let's start transforming the integral by using this trigonometric substitution. We are using 5x equals 2 times secant theta. So you should be careful. Instead of just having x here, x squared, we have just, we need to write 5x squared. And a is 2, that's why the substitution looks like this. So compute dx, or take the derivative of each side. What is the derivative of secant function? It is secant theta times tangent theta d theta. Now, let's transform the integral. Instead of dx, what should I write? I should write 2 over 5 times secant theta tangent theta d theta. This is written for denominator, which is just dx. Okay, and what we have at the denominator, let's see. At the denominator, we have 5x squared, right? So that's why square of this thing minus 4. Like this. And what is this thing here? Take 4 parentheses out. So what is secant square theta minus 1? We know that it's the famous trigonometric identity, remember? Okay, let me put a recall here about that. Secant square theta is tangent square theta minus 1, or you can write it in the tangent square form like secant square theta. So this is plus and this is minus. We use it here. So the integral is what? Let me rewrite it, the denominator part. Secant theta, tangent theta, d theta. And at the denominator, we have square root of 4 tangent square theta. That's why it is just 2 times tangent theta. Okay, then simplify things. This is gone, this is gone, and these two are gone. So that we have just 1 over 5, it goes out. And in the denominator, we just have secant theta. By the way, okay, obviously you do not simplify the theta, yeah. Okay, tangent thetas are gone, 2's are gone. We just have this after simplification. So the result is 1 over 5. The integral of secant theta is given by this rule, secant theta plus tangent theta, and then you need to add this arbitrary constant c. It is time to turn back to your original variable x now by using your reference triangle. Okay, what's the reference triangle here? Let's draw it to this part. So our reference triangle is drawn by using this first line. So here, what do you read about secant theta? Secant theta is 5x over 2. So secant theta is read as 5x over 2. So secant theta is in fact 1 over cosine theta. That's why cosine theta is 2 over 5x. And this trigonometric information is enough to draw a reference triangle here. We will draw a very nice right triangle where this angle is theta, then cosine means opposite edge divided by, adjacent edge divided by the hypotenuse. That's why the opposite edge is computed as 25x squared minus 4 square root. So look at your result. 1 over 5 ln, what is secant theta? You see already secant theta is 5x over 2. And you can easily read tangent theta from this reference triangle. What is it? Opposite edge should be divided by adjacent edge. So it is 25x squared minus 4 square root divided by 2. And that's it. That's how you should turn back to your original variable x by using this reference triangle, okay? So at the end, you have to use this reference triangle to turn back to original variable x. And I stop here. Thank you for your attention.